Assalamu alaikum. Previously we have discussed about the binary isomorphous system. Now in this lecture we will discuss about the binary eutectic system and what is the difference between isomorphous system and eutectic system, and what is the eutectic reaction and when the eutectic reaction takes place, determination of phases, phase computation, and we will solve some numerical problems, and we will solve the microstructure of the eutectic alloys, development of microstructure in eutectic alloys. A eutectic or eutectic mixture is a mixture of two or more phases at a composition that has lowest melting point that has a lowest melting point. It is where the phases simultaneously crystallize from molten solution. The proper ratios of phases to obtain a eutectic is identified by the eutectic point on a binary phase diagram. The term comes from the Greek letter eutectos, meaning easily melted. So a eutectic or eutectic mixture is a mixture of two or more phases at a Here is the example of one figure, a generalized figure for the eutectic phase diagram. The phase diagram displays a simple binary system composed of two components A and B, which has a eutectic point. This point is called eutectic point. At eutectic point, the parallel line, the temperature is called eutectic temperature. So this is a lowest point. If we look at this point, this is the lowest common points between the two different liquids and solids. So this is another liquidus line of solution B. This is a liquidus line of solution A. So if they are melted in each other, the lowest point of, if they are mixed with each other, the lowest point which is reached is this point between. If we go above the temperature increases for the both of the solutions. That's why a common melting point, lowest point, eutectic point is this one. Over here in this region alpha solid solution, in this region beta solid solution, where in this region we will define all these boundaries in the region between the liquidus line and solidus line, a mixture of solid and liquidus line, alpha plus beta solution. Over here alpha plus liquid solid B, beta solidus beta, while below eutectic point the solidification of both the solids occurs, solid alpha plus beta occurs. So we will explain the microstructure of eutectic point, just like previously we have explained the copper nickel slow cooling from 1300 to below. So similarly we will study the microstructure of the eutectic phase diagram with respect to the mechanical properties. Binary eutectic systems. We are repeating this section because we want to study the microstructure of the binary eutectic systems when it is cooled down from a specific temperature in different regions. Binary means two components. Eutectic means has a special composition with a minimum melting temperature. First, three single phase regions are found on the diagram: alpha, beta, and liquid. Alpha, beta, and liquid. First, three single phase regions are found on the diagram. One is alpha, beta is to the right hand side, and liquid is above the melting point, above the eutectic point. The eutectic point is E, and the other mixed two phase regions how many we can identify how many two phase regions. One is alpha plus liquid, the other is beta plus liquid, the third one is alpha plus beta, both solids. The alpha phase is a solid solution rich in copper. It has silver is solute component and FCC crystal structure. This one is the alpha region. From A to C, from point A to C is the alpha region. A, B, C is the curve A, B, C is the alpha region. The beta phase solid solution also has FCC structure, but copper is solute. Pure copper and pure silver are also considered to be alpha and beta phases respectively. For the beta region, which is a pure solid solution, is represented by the line F, G and H on the right hand side. In the horizontal axis, the composition is changed gradually from 0 to 100%. It is a silver copper solution. The liquidus line is represented by A, and E to F. The solidus line, which separates the solid solution from the mixture of crystal plus solid, is AB, the solidus line. The solvus line is line B to C. The solubility in each of these solid phases is limited, and that any temperature below the line BEG, before we explain what is below the line BEG, what is the temperature, what we call it to be the temperature at parallel to BEG. This is the eutectic temperature. Below line BEG, only a limited concentration of a silver will dissolve in copper for the alpha phase, and similarly for the copper in silver for the beta phase. The solubility limit for alpha phase corresponds to the boundary line labeled CBA. CBA. This is the solubility line, solubility limit for the alpha phase. Between the alpha plus beta and alpha plus liquid phase regions, it increases with the temperature to a maximum of 779 degrees centigrade with the 8% of the copper over here at point B, the maximum solubility limit. This is the and decreases back to zero at the melting temperature of the pure copper, which is below 400 degrees centigrade over here. This is the solubility limit. Maximum is point B, starting from point C. Suppose if we cool down, then it's starting from point B until point C, which is the melting point of melting temperature of the copper. So similarly, at temperature below 779 degrees centigrade, the solid solubility limit line separates alpha and alpha plus beta phase regions. The solid solubility limit. So this line is called a solvus line because it separates the alpha plus beta phase region from the solid line. The boundary line AB between the alpha and the alpha plus liquid fields in the solvus line is indicated by the line BC. The maximum solubility of copper in beta phase, which is point G, has 8.8% copper, also occurs at 779 degrees centigrade. This horizontal line BAG, which is parallel to the composition axis and extends between these maximum solubility position, may be considered a solvus line. It represents the lowest temperature at which the liquid phase may exist for any copper silver alloy that is at equilibrium. As silver is added gradually to the copper on the horizontal axis from 0 to 100%, the alloy become totally liquid, decreases along the liquidus line. Line AE, which is the liquidus line, is the alloy at this point, the AE. The alloy become totally liquid, decreases along the liquidus line AE. Thus, the melting temperature of copper is lowered by silver addition. The same may be said for the silver. The introduction of copper reduces the temperature of complete melting along the other liquidus line EF. So, both melting temperatures are decreased to the minimum melting point as they are added with each other. A composition limit is reached where both the solvents reaches at minimum melting point, which is a eutectic point. So the line these liquidus line meets at a point E on the phase diagram, the which through which also passes the horizontal isotherm line BAG. Point E is called invariant point as well, which is designated by the composition CE in temperature E, 71.9% by weight of silver, and the temperature is 779 degrees centigrade at this invariant point. So we will explain in the next slide. We will explain the eutectic reactions, the which is an important reaction which occurs for an alloy. The eutectic reaction which will occur upon cooling and heating at a specific temperature and upon specific composition. Upon cooling, a liquid phase is transformed. Upon cooling, a liquid phase is transformed into two solid alpha and beta phases at a temperature TE. The opposite reaction occurs upon heating. This is called the eutectic reaction. Eutectic means already discussed, easily melted. And C, the point C, E, and TE represents the eutectic composition and temperature. The eutectic composition is CE in the liquid phase upon cooling transformed into alpha and beta phase. C alpha for solid for the alpha, composition of solid for alpha, while C beta is the composition for solid of solid for beta. So the liquid is transformed into two solid phases. One is alpha, the other is beta. Similarly, in reverse, the reaction, if both are combined upon heating, both the substances is converted into liquid with the composition, with this composition it which is mentioned at point E. C alpha E and C beta E are the respective composition of alpha and beta phases at temperature TE. Thus, for the copper silver system, the eutectic reaction occurs as follows. The liquid at a composition of 71.9% weight of silver upon cooling transformed into alpha at 8% weight of the silver plus beta at 91.2% weight of silver, which is represented in the phase diagram, eutectic phase diagram. Thus, the eutectic reaction upon cooling is similar to the solidification for pure components, and that the reaction proceeds to the completion at a constant temperature or isothermally at TE. However, the solid product of eutectic solidification is always two solid phases, whereas for the pure component only. Here we summarize the discussion for the eutectic reaction for the copper silver solution. The solvus lines are BC and GH. One is for the alpha, the other is for the beta. The solidus lines are AB, FG, and BEG. These are the solidus lines, FG and BEG, which is the summary for the solidus line, and they are called the eutectic isotherm. The liquidus line is AEF. AEF is the liquidus line. Maximum solubility of alpha is 8% by weight of silver, while maximum solubility for beta is 8.8% by weight of copper. Invariant points are three phases where the points where three phases are in equilibrium. The point E is the invariant point. We can also call it eutectic point. At this point, CE is 71.9% weight of silver and TE is 779 degrees centigrade. An isothermal reversible reaction between two or more solid phases during the heating of a system where single liquid phase is produced. This is called the isothermal reversible reaction. It occurs between two solid phases during the heating of a system where a single liquid phase is produced. Concept check. At 700 degrees centigrade, what is the maximum solubility of copper in silver, of silver in copper? So you can go to the website which is mentioned over here, but the in copper silver phase diagram you can go through 700 degrees centigrade, draw a parallel line and then check about the solubility. First find out the region, phase region, and then within the phase region just find out the calculate the maximum solubility, the calculate the maximum solubility of copper in iron and then of iron in copper. Concept check 9.5. The following is the portion of water and sodium chloride phase diagram. Number one question: using this diagram, briefly explain how spreading salt on ice, that is at a temperature below 0 degrees centigrade, can cause the ice to melt. At what temperature is the salt no longer useful in causing ice to melt? So you can go to the website and find out the answer by yourself. It's your home assignment. Problem 9.2: determination of phases present and computation of phase compositions. This is a solved example in the book of Celester, book of engineering material written by Celester. The problem statement is for a 40% weight, 10 and 60% lead at 150 degrees centigrade, what is, phases are present, what is the composition or compositions of phases. In solution, we have a given data that a 40% weight, 10 and 60% weight, and a given lead 10 diagram is given in exam. This diagram, the phase diagram, will be given. So at 40% weight, locate the 40% horizontally. The C1 is located horizontally. Draw a vertical line until it reaches the 150 degrees centigrade, so that we got a point B. The point B is the point at which we want to find out the phase, the present, find out the region, in which region this point B is located. This point B is located in the region of alpha plus beta, two phase composition, solid composition. So this temperature, the it is within the region both alpha and beta phases are existing in this region. So the answer is alpha and beta phases are present in this region. Both alpha and beta phases will coexist. So now in part B, what is the composition or compositions of the phases? This point B, at this point, both a mixture of alpha plus beta is present, but how to find out the composition? Draw a tie line. A tie line is drawn from point B so that it crosses, it reach alhamdulillah. A tie line is drawn from point B so that it reach the Salvage line of alpha and the Salvage line of beta, and draw perpendicular from the boundary lines of Salvage line and of alpha and beta. The Salvage line from alpha is C alpha. The Salvage line from the tie line, the intersection of the tie line and the Salvage line of beta. This is the solution of part B in problem 9.2. Because two phases are present, it becomes necessary to construct a tie line across the alpha plus beta phase field at 150 degrees centigrade as indicated in figure 9.9. The composition of alpha phase corresponds to the tie line intersection with the alpha or alpha plus beta Salvage phase boundary. About 11% weight, 89% weight of lead denoted as C alpha. Similarly for beta phase, which will have a composition of approximately 98% weight 2% weight of lead C beta. Find out the C beta. So C beta is the answer for C beta is 98% weight 2% weight lead. The answer for C alpha is 11% weight 89% weight lead. This is the required answer. In exam, the question may be changed to find out the composition, say at lead 60% lead, 40% tin. Find out the composition at that point and find out the phase region. How many phases are present? In exam, the question may be changed to find out a composition and phases. Relative phase amount determinations, mass and volume fractions. This is in another problem 9.3. The statement is for the lead tin alloy in example problem 9.2. Calculate the relative amount of each phase present in terms of A. Mass fraction, B. Volume fraction. So far we have solved the questions related to the mass fraction, but in this problem we will solve the problem related to the volume fraction. At 150 degrees centigrade, take the densities of lead and tin to be 11.23 and 7.24 gram per cubic centimeter respectively. For the volume fraction, we need the densities. The densities are also given. The rest of the formulas are same as in the previous labor rule formulas. The only change is instead of mass fraction, you have to give the answer in volume fraction. So this is a solved example. Go through this example 9.3, the solved example, and solve it by yourself. Development of microstructures in eutectic alloys. Depending on composition, several different types of microstructures are possible for the slow cooling of alloys, which belongs to the binary eutectic systems. So these possibilities are considered in the subsequent slides, in which the composition is changed from one point to the other point, just like in a given example. In this slide we will explain the microstructure of slow cooling of substance at C1, composition C1 at the W, at the line W prime. So at this in this range, for alloys between composition less than 2% by weight of 10, the result will be at room temperature is polycrystalline with grains of alpha phase having composition of CO. The composition of CO at this point is C1, not CO. The composition is polycrystalline when cooled below 300 degrees centigrade at point C. Small alpha grains are found. Now consider an alloy of composition C1. This is the case for the composition ranging between a pure component and the maximum solid solubility for that component at room temperature, which is 20 degrees centigrade. For the lead tin system, this includes lead rich alloys containing between 0 to about 2% weight, 0 to about 2% weight of tin, and also between approximately 99% weight of tin and pure tin. For example, in this one over here, this alloy at C1, when it is slowly cooled from room temperature within the liquid phase region, which is 300, suppose 350 degrees centigrade, say at point A. When this is cooled, this corresponds to moving down the dashed vertical line WW prime in the figure. Over here, this one is the C1 to WW prime line. The alloy remains totally liquid in composition of C1. This one alloy remains totally liquid. The microstructure is totally liquid at this point. As soon until we cross the liquidus line at approximately 330 degrees centigrade, approximately 330 degrees centigrade, at which time the solid phase begins to form. At point B, at about 330 degrees centigrade, the solid phase begin to form. If we look at the microstructure at point B, some small grains of solid particles begins to form. These are the small grains of the crystals of which begins to form. So while passing through a narrow alpha plus liquid region, this is a narrow region, alpha plus liquid region, solidification proceeds in the same manner as was in the at point B. So until the solid phase begins to form, until we reach a point, we cross the solid line, the boundary of alpha plus liquid region. As soon we cross the alpha plus liquid region, we can get a solid grain particle, polycrystal, just like point C, say at a temperature between the 300 and 200 degrees centigrade. If we look at the microstructure, all grains or solid grains of alpha with the given percentage. Solidification proceeds in the same manner
but no further improvement in the solidification occurs as the boundary of the alpha plus liquid range is crossed. Furthermore, liquid and solid phase compositions are different, which follows along the liquidus and solidus phase boundaries. The resulting alloy after crossing the solidus boundary is polycrystal with a uniform composition of C1, and no subsequent changes will occur after this point and within the whole region of the solidus point. Development of microstructure in eutectic alloy is a second example. In this example, the lid tin system, the composition extends from about 2% weight of tin to 18% weight of tin, which is represented by the point C, to 18% weight of tin, 18.3% weight of tin, and from 97.8% weight of tin to approximately 99% weight of tin for tin rich alloys. Let us examine an alloy of composition C2 as it is cooled along the vertical line x prime. In this figure, this is figure 9.12 in the book of written by Celester. The line is drawn from x to x prime, and the points of interest are the microstructure at point D, E, F, and G. Similar to the previous example, at the liquid region, the microstructure at the liquid phase remains the same, which is at a temperature about 350 degrees centigrade. This microstructure will be the same until we reach the boundary of the liquidus line. But as the boundary of the liquidus line is crossed, changes that occur are similar to the previous case, but as we pass through the corresponding phase regions, as demonstrated by the points D, E, F, these points just above the salvus intersection, just above the salvus intersection at this point F, the microstructure consists of salvus line is this one, the downward one, just above the salvus intersection point F is this one. The microstructure of the salvus line consists of the microstructure of the at point F consists of alpha grains of composition C2. Upon crossing the salvus line and alpha solid solubility is exceeded, which results in the formation of small beta phase particles. These are included in the microstructure inset at point G. Small beta particles, you can see when the salvus line is crossed after this point. At the salvus line, within the solid alpha region, if we compare the microstructure which is mentioned over here, all solid grains, alpha grains are mentioned, the grain with no components of beta. But as soon the salvus line is crossed at this point and at this temperature over here below 200 degrees centigrade, the formation of beta particles begins to form. Some small beta particles are mentioned by the blue dashed lines within the alpha particles. So with the continuous cooling, these particles will grow in size because the mass fraction of beta phase increases with the increases slightly with the decreasing temperature. So this is the microstructure of at point C at a percentage weight of 18.3. Initially at a liquid state at point D, the microstructure is completely liquid. When we cross the liquidus line, and at point C, within the liquid grains, the solidification starts. The mixture of alpha and liquid phase exists in that microstructure level. Surround the small solid grain particles are surrounded by the liquid particles, and as soon the solid line is crossed and we reach the solidus line, the small grain particles are completely solid and no liquid particles are exist at point F1. But after the solidus line is crossed, some beta particles begins to form the beta grains, as shown at the microstructure of point G. Now we will discuss the third phase, the third example for the development of microstructure in eutectic alloys. The third case involves the solidification of the eutectic composition, which is 61.9% 10 C3 which is located by C3 in the figure over here. 61.9% 10, which is directly passing through the eutectic point, or invariant point we call it, and this point is represented, this composition 61.9% composition is represented by a straight line y prime over here, y prime. The component is the alloy is solved from the melting point, from the melting state, say at a temperature of 250 degrees centigrade, at which the liquid state is still homogeneous, and the microstructure of the liquid state is with the 61.9% by weight is all the grains or particles are in the liquid phase. So now as the temperature is lowered, no changes occurred until we reach the eutectic temperature 183 degrees centigrade. So once the cooling occurs, no changes occurs after the cooling until we reach the point over here at the eutectic temperature, which is 183 degrees centigrade. Upon crossing the eutectic isotherm, the liquid transforms to the two phases. This transformation may be represented by this reaction. The liquid transformation into two phases is this one, alpha plus beta. And this transformation is represented by this reaction, in which L liquid phase at 61.9% by weight. Upon cooling, it is transformed into alpha plus beta. Alpha particle with 18.3% by weight of 10, and beta particle with 97.8% by weight of 10. How can we determine this percentage? Again, when this is crossed, just like the tie line is already the isotherm temperature, and the isotherm temperature at the minimum phase is which is starting for this one is 18.3 for the alpha, while the composition for the changes to solidification to beta is 97.8% by weight is this one. So or in reverse reaction, if both alpha and beta particles are heated, upon heating it is again transformed into the liquid phase with this one, with 61.9% by weight. In this reaction, the alpha and beta phase compositions are dictated by the eutectic isotherm endpoints. During this transformation, there must be necessarily be redistribution of the latent components in as much as the alpha and beta phases have different compositions, neither of which is the same as that of the liquid. This redistribution is accomplished by atomic diffusion. The microstructure of the solid that results from this transformation consists of altering layers, sometimes called uh, lamellae. We will discuss the lamellae in the subsequent slides. This is the microstructure of the two solid phase alpha and beta. The alpha is represented by the pink lines, while the which is surrounded by the blue lines, beta particles. Alpha is 18.3% by weight and beta is 97.8%. Lamellar eutectic structure. In the previous slide, when the alloy is cooled down from a temperature of 250 degrees centigrade at composition equal to Ce at 61.7% by 61.9% by weight was upon cooling and upon crossing the isotherm temperature, the results in the eutectic microstructure with altering layers of alpha and beta crystals, which is called lamellar eutectic structure. A two-phase microstructure over here. This is the magnified grain size of the lamellar structure. A two-phase microstructure resulting from the solidification of a solid having the eutectic composition where the phases exist is the lamellae that alternate with one another, uh, like beta over here and then alpha beta and then alpha alternate with one another. These one, the eutectic growth direction occurs in this one. This shows the eutectic growth direction. Formation of eutectic layer microstructure in the latent system during solidification at the eutectic compositions of alpha and beta phases are very different. Solidification involves the redistribution of the latent atoms by the atomic diffusion.
This is a lead tin microstructure in which the dark layers are the lead-rich alpha phase, while the light layers are the tin-rich beta phase. The dark green, these are the dark region over here. The dark regions, there are just like lamellar structure. Lamellar structure is produced over here, while the light layers, these are the light layers which are the tin-rich beta phase. Here we discuss some applications of the lead tin alloy, some important materials, lead-free solders. In the table is given, in this table the composition of weight percent by for the lead tin alloy at solidus and liquidus temperature is mentioned. So these are the composition solid. This table represents the composition, solidus temperatures and liquidus temperature for 5 lead-free solders. Solders, because it is important to discuss about the applications of the lead tin alloy, because solders are very important that we are using to for the bonding or joining two or more components. They are used extensively in the electronic industry to physically hold assemblies together. Furthermore, they are also allow expansion and contraction for the various components. And also they are using for the heat generation. When the heat is generated, so they expand and they prevent the material from the damaging the bond between these two materials. So the bonding action is accomplished by the melting the solder material. This allows the flow among the the two materials and make contact with the components to be joined. So these composition which is mentioned over here in this table, this provides some important the percentage of the lead tin Li. The tin is 52% by weight composition, and solidus temperature is 118, while liquidus temperature is also 118. For these particular lead tin Li, these provide us the application for the solders.